Welcome back. Dr. Pitcher here, and in this video we will take a look at the acidity of alcohols. So, alcohols are weak acids, but this should be, it should be noted that this is compared to other aqueous acids. So something like HCl, H2SO4, CH3COOH, so things like that. They're actually pretty strong acids, or we'll say relatively strong acids. When we compare them to a lot of organic molecules. So for example, let me write it like this, ROH, my pKa is going to be around 16, okay? And that's for that hydrogen, of course. Now, normally in water, that hydrogen won't be deprotonated, won't be able to pull it off. But if we had a strong base, like let's say lithium diisopropylamide, LDA, that could pull that right off. Sodium hydride, the hydride would pull it right off. And acetylide would pull that right off. So, you know, just by comparison here, a few other we have a pKa of 20 for one of those guys. Our acetylide has a pKa of 25. Something like an amine has a pKa of around 35 or 36. And then something like a regular alkane has a pKa of around 50. So think back to pKa and what that represents. And so if I had an equilibrium between, say, you know, this guy and an acetylide ion, it would favor the weaker species. So an acetylide ion would pull a proton off and give us our alkoxide from our alcohol. So these are relatively strong acids to a lot of the reagents, especially the Grignard reagent, which we will see, see in a little bit. But compared to things like acetic acid, sulfuric acid, hydrochloric acid, they are weak acids. Now, you can take a look at table 17.1 for some pKa values of different acids, or sorry, different alcohols. But pKa of H2O is actually 14. So this is a correction that textbooks are starting to make. McMurray did not make it. The Klein text actually does make it. It lists the value of 15.7, which is traditionally what organic chemists have used as their pKa for water. But it says that there's actually more evidence that says really it should be 14. And that makes sense because that was the pKw of water. And pKa, kind of, it is pKw except when, you've got something that's not water. Anyway, long story short, I could show you the math and how you get 15.7 for the pKa of water if you really want me to. But I just thought I'd mention this. The pKa of water is actually 14, not 15.7. And that actually is consistent with one of the general properties of alcohols. So the structure of the alcohols affects acidity. So for example, T-butanol has a pKa of 18. Ethanol has a pKa of 16. Methanol has a pKa of 15.3, 15.25. So the reason for that is actually the steric hindrance from the alkyl chain. And so it would make more sense that water, which is smaller, has no steric hindrance, would have a lower pKa, since that's the trend that we see. Let me just write that in here, CH3OH, 15.25. We could have, let's say, we could stick some fluorines on our, so we could have like trifluoroethanol. That pKa would be lower. Interestingly, thiols, I'll just write this in here, CH3SH, methane thiol. I'm not going to talk about thiols. You can read about them if you want to. They are in this chapter. I might talk about them some next semester, I think. But I just realized this is wrong. I got those numbers backwards. It's 15.54. Sorry about that. 15.5. Round. All right. This is 10.3. So you can see that the difference having a sulfur instead of an oxygen results in difference about 4 pKa units. So the sulfur, the negative charge in our conjugate base is much happier on the sulfur. We could have something like phenol. We'll just use the circle in the benzene ring. And the pKa of that is 9.9. And that's due to the resonance stabilization of the benzene ring. Now, if we had substituents that were electron withdrawing, we'd get more of a withdrawing effect, an inductive effect. And, for example, paranitrophenol would actually have a pKa of around 7. Now, you want to watch out for these you want to watch out for the fact that alcohols are acids when it comes to organic reactions. So, sorry, I knocked over my little guide here. This is so I don't have to keep checking to make sure I'm in frame here. So, I'm just going to say, remember to check for acidic species, for example, alcohols, in reactions with strong bases. So what are some examples of this? Well, for example, if we wanted to do RC triple bond C minus plus, let's just do, let's do CH3Br Now if we do, now let me write this a little differently. Sorry about that. RC triple bond C minus, and we want to add CH3Br. We wouldn't want to use ethanol as our, methanol as our solvent, because what we would get is RC triple bond CH plus CH3O minus plus CH3Br. Oops, we didn't methylate our acetylide, and that's because our alkyne is even less acidic than the alcohol is. So really we're looking at an equilibrium between base, acid, conjugate base. And so our acetylide ion is a stronger base than our methoxide ion. Our methanol is a stronger acid than our acetylene. So the weaker species is where we will get equilibrium. Similarly, if we tried something like RMGBr, and we tried to do that with, so I tried to add it to acetone, but we used methanol, we would end up with RH plus CH3O minus MgBr plus, and we'd end up with this salt, plus we'd still have unreacted acetone. So my point is, you want to watch out for the alcohols getting in the way. So you always need to think about what functional groups are present. And usually we just have one functional group in a given molecule, but you wouldn't want to, say, have two different compounds. So use something like methanol as your solvent when you're trying to do a Grignard reaction. And in a couple of lectures I'll talk about the Grignard reaction and the fact that we use ethers instead of alcohols or instead of acetone, things like that, when we do the Grignard reaction. All right, so let me see here. Was there anything else I wanted to say about, I don't think there's anything else I wanted to say about the acidity of alcohols. But just remember, they are decent acids as far as a lot of organic compounds are concerned, even if they're weak acids compared to things like HCl and H2SO4. All right, so until next time, stay safe out there. Bye now.